So welcome everyone. Takes a while for the participants to get added in. So we're going to give them a minute to join us. My name is Nathan and I'm joined by my colleague Daniel. Good morning, Daniel.
Good morning, Nathan.
And if you're on the East Coast and it's afternoon, good morning to you. We are just about to get started. The numbers keep climbing here, so I'm going to let a few more people trickle in. This training is part of Briggs & Stratton Energy Solutions Elite Installer Training. It's on maximizing solar energy using battery storage, and we're going to get into some of the basics on solar panels and how you can use batteries to produce more energy. As we get started, I just want to let you know that I don't have the ability to unmute you, so raising your hand won't help. We need to have you use the Q&A section. So go ahead and use Q&A, ask questions if you've got them, and Daniel will try to respond to some. And Daniel, please stop me if there's some good questions that should be addressed as I'm speaking.
Absolutely.
So once again, welcome everyone. The numbers seem to have stabilized here, so I'm going to go ahead and get us started. As I mentioned, I'm one of the trainers here at Briggs & Stratton Energy Solutions, and I'm joined by my colleague Daniel, also a trainer with Briggs & Stratton Energy Solutions. All right, so Briggs & Stratton acquired Simplify Power a little over a year ago now, about a year and a half ago. And Simplify Power has a long history of making battery solutions for the home. We got started as optimized energy storage back in 2010, and 13 years might not sound that long, but my colleague Daniel often puts it in perspective for people that, you know, the Powerwall wasn't even released until 5 years after that in 2015, right? So we've been doing this a long time. And we have some principles that we operate on. One of them is safety. The safety is extremely important to our company, to our battery solutions. And because of that, we use only cobalt-free chemistry. We use lithium iron phosphate chemistry. We're not going to talk a lot about chemistry here, but you should know that lithium iron phosphate, instead of using a cobalt-based chemistry for the cathode, we're using iron. Makes the batteries a little bit heavier, but much safer and gives them a longer lifetime, and basically gives you the ability to get more out of those batteries and have them last for a very long time. We essentially also have no risk of unmitigated thermal runaway, right? There are a lot of different types of lithium ion batteries, and the battery that we use essentially does not have these fire problems that can be seen in batteries that may be involved in a car crash, and you see a car that's burning and they can't put it out, or these phone batteries that you've seen catch on fire. With an LFP battery, we actually publish our 9540A tests, which involves forcing a battery into a fire. And you can get those results on our website, and the spoiler alert, there's not much that happens. Essentially, these batteries put themselves out. So there's a bit of smoke and there's off-gassing, and that does occur. But again, you don't have this thermal runaway potential. And when you're putting something in your house, that's extremely important that it's safe. But don't trust us, right? We have external testing that's done. We are certified with UL 1642 at the cell level, UL 1973 on the battery module level, and then 9540A on some of our system levels. We also have the UN Department of Transportation certification 3480, allowing us to transport our batteries, and UL 38.3 on some of our batteries, which allows us to airship them. Another principle of operation for Simplified Power is that we offer simple solutions. We easily integrate into almost any different generation source. We store energy for critical backup and power, and have easily integrated into other equipment. So one of our things has been being inverter agnostic, being able to easily pair with other equipment. We maximize resilience and energy security by doing this, right? By giving people access to battery backup. They have access to power when they need it, and it allows them to generate their own power, giving them some energy security. This allows them to save on their utility bills, and we'll talk about some ways to use batteries to do time of use, peak shaving, and demand charge management. I'm not going to spend a lot of time on this, but we're proven. We're a US-based manufacturer. We do our battery builds out here in Oxnard, California. We've been doing that the entire life of Simplify. We are deployed in over 45 countries worldwide. We have over 300 megawatt hours installed. We've done testing and validation with the US Army and Marine Corps. So we were back in 2011, we were approached by the Army, and we were able to show them that lithium batteries can be safe. They can be safe and they can be durable, and they are, we've been deployed as well. Business model, we have a business model that demonstrates social impact and profitability can coexist, and we have a program that we call the IDEA program, and we're often supporting projects through donations, typically battery-based donations. So highlighting this, we are international. We have distributors around the world selling our products, Australia, India, Africa. Of course, most of our sales are in the United States, but we are branching out into other locations as well. We've been deployed across many different countries. And some of our battery solutions products look like this. We have outdoor rated battery cabinets. We call that our access cabinet in the upper left. There you see it situated with a Solarc. We have BOSS cabinets, which are waterproof outdoor NEMA 3R rated cabinets. We have mobile solutions, and we even have a whole line of high voltage products that you may not be aware of. So if you're doing large scale projects, keep us in mind. We have a whole team of engineers that work on that. Again, this talk is not going to be about chemistry and the internals of batteries, but know that we use the safest lithium ion chemistry, that's LFP, lithium iron phosphate battery chemistry. And we use cylindrical cells, which are the most expensive, but also the most durable and longest lasting cells on the market. And so we're able to offer a very strong 10-year, 100% depth of discharge, unlimited cycle warranty on our batteries. And that's pretty much one of the best in the industry. And we expect our batteries to perform better than most of our competition because we're using premium cylindrical lithium iron phosphate battery cells. Batteries give customers a way to use solar energy or energy that's generated in other means to do a number of different things. So one thing that you can do with batteries is peak shave. So power companies are creative in the way that they charge customers, and one of the things that they'll often do is charge customers based on how much peak demand that they're utilizing at any instant in time. And so if you are only going to a high power draw, maybe you're drawing 100 kilowatts, but only for a very short time, you'll end up getting these high demand charges in some instances. And a lot of customers will talk to us about how to reduce those demand charges, and batteries are a way to do that. You can also get time of use rates. And so electricity rates typically in the evening time, especially depending on where you are. In California, we have a lot of higher rates in the evening times. And so I can pay above 40 cents per kilowatt hour in the evenings when I'm using power. That typically that's when people are getting home from work and solar becomes less and less available. If you have batteries, you can avoid some of those time of use rates. You can charge your batteries and discharge when you need that power. And then also, if you do have solar, you have integrated solar and storage, it allows you to generate the power when that solar is available and use that energy when you're ready to use it. Maybe you generate excess power in the day and use that excess power after you've stored it in the evening time. So these are probably not new concepts to many of you.
And
Daniel,
Nathan, yeah,
ahead.
one of the points I wanted to make about the last one is that with the new net metering agreements coming down, especially here in California, and it's not just California, these new net metering agreements are going to be coming to other states, that you no longer get the same credit, right? So during the day, you could theoretically send power to the grid, get a full credit for that, then use that credit up at night or in the winter. With the new net metering agreements, you no longer get a full credit. So in a way, this battery systems allows you to capture that solar production during the day. And then rather than sending it back to the grid for a fraction of a credit, you now can keep it, store it, and use it later at the date. So I think storage is really going to start to justify and give people a financial reason to go with solar now.
Yeah, thank you, Daniel. We're going to talk about that a little bit. And I know not everybody on this call is from California. We certainly have an international audience in almost every one of these webinars. However, what often happens in California seems to spread around the country, and many places you don't have that opportunity to feed back. So what Daniel is talking about is currently in California, we're now in a NEM 3, a net energy metering 3.0, which really takes away those feedback rates that you used to get. So you used to get full retail value for the energy you would feed back onto the grid, and that's been reduced by almost 75% in many cases. And you also have to pay a grid connection charge now. And so batteries make a lot of sense for those that have solar, especially when you don't have good feedback tariffs or coming from your utility provider. So let's talk. We're going to go through the basics of solar energy, and I'm imagining many of you are already familiar with some of this stuff, but hopefully we can get into some of the details and find ways to be able to present this information to customers as well. So let's look at the typical energy production with home solar arrays. So probably the most common is rooftop solar, right? And this could be AC coupled or DC coupled. So an AC coupled system would have microinverters on it, and you're sending that AC voltage down off the roof and to your load center. These are almost always fixed orientation, but sometimes there will be several strings with different directions. You might have an array pointing east, south, west, or if you're in the southern hemisphere, north, right? The idea with this is typically that you're matching the shapes of the roof that you're installing on. And I'm getting ready to put one on the south face of my roof as well. If you have the space, so in more rural settings, people often choose to do ground mount because there's no need to remove the panels when you're having your roof redone. And of course, there's not that potential to have leaks. Ground mount solar typically is DC coupled. Oftentimes there's just a single fixed orientation. Typically all panels are in that same orientation. And there are some advantages to ground mount, especially in terms of cost, right? It's much easier to do the installation where you're not having to go to a roof. So here is a typical roof mount production curve. So this is actually an install that I did together with students and a local contractor. Those are 2,425 watt panels, so an 8.5 kilowatt array. And I'm showing you production out of this array a couple months ago now, I guess. So back in March. And if you look at that, that's an 8.5 kilowatt array or a little over 8 kilowatt array. And what you'll notice is that it peaks out at less than 6 kilowatts of AC production. And so I'm going to get into why that is the case a little bit today and talk about how we can use batteries to generate more power. You can see that this is a pretty clean day, meaning there was not a whole lot of clouds. You can see some dips in the energy production there, but this is a fairly typical curve. I should also note that this system is just a grid-tied system. And it's a DC coupled string inverter with 2 strings of panels, and it's feeding directly back to the grid. This was done under NEM 2.0. But there are variations in the output power of solar arrays, right? Solar arrays are almost always producing less power and energy, less power than what they're rated for, less power than rated power. And forgive me for mixing the word energy there on the screen. So why is that the case? Why do solar panels produce less power than their rated power? Well, there are a number of things that go into that. Temperature, right? So typically panels produce more power at lower temperatures, and as panels are black, when they're in the sun, they heat up. The ratings on the panels is based on a temperature of 25 degrees Celsius, but most panels are operating at temperatures well above that unless it's a very cold day. Also have shading issues, right? So if some of the panels are partially shaded, you can end up with needing to use bypass diodes, which reduces the voltage of the string. Orientation of the panels is a big one, right? So I'll talk about how panels produce the most amount of energy, obviously, when they're perpendicular to the sun. But there's also other orientation effects that matter too, just time of day, season, etc. So maximum power point tracking, right? It's also when the panel is producing energy, it's the job of the electronics to track that maximum power point. I'll talk a bit about that. And then there are the efficiencies of the equipment, which is turning the energy coming out of the solar panels into typically AC power. And of course, we have drops along the lines, etc., etc. Weather is a big one. So weather influences obviously the temperature influences the panel, but cloud cover, of course, as well. In California, this time of year, I'm very close to the coast, and we get a lot of kind of hazy mornings where we've got fog cover coming from the Pacific Ocean, which is pretty cold. And then that time of year is a big one. So this is not really a talk about how solar energy is being produced and getting into all the angles, but I wanted to briefly show you this graphic. This is a graphic that I created for students several years ago when I was teaching an introductory physics class. And this image shows a number of things. So it shows the Earth going around the sun in different times of year. So look at that picture and see if you could identify which position on the screen would be summer, just based on the orientation of the Earth, right? So which one would it be? 1, 2, 3, 4. Okay, so if you look, yes, Daniel. Go ahead.
It would be number 3.
Number 4.
Number 4.
Right? So when the northern hemisphere, so the Earth is tilted at a 23-degree angle, and when the Earth is evolving, rotating around the sun, right, orbiting around the sun, when the North Pole is pointed the most directly towards the sun, right, the northern hemisphere is getting longer days, right, and you're getting more direct sunlight. So typical solar arrays will produce a lot more energy in the summer than they do in the winter. And the farther north you go, the more pronounced that effect is. And it has to do with the panel orientation, but of course it also has to do with the length of the days, right? And so if you look, the diagram also shows that Earth kind of rotating on the axis. And if you consider in position 4, the Earth spinning like this so that the Earth is headed towards the east constantly, that's why the sun rises in the east. The shaded portion there indicates nighttime. And so when you're on a place in the Earth that is not in the shadow, right, you are in daytime, right? And so you can see that when you're going around the Earth in the northern hemisphere there, your days are going to be longer. And in fact, if you're on the North Pole or if you're beyond the Arctic Circle, you have constant daylight in the summertime. And then as the Earth goes around, you'll have fall, and then winter, the northern hemisphere is tilted away and your days are going to be shorter. If you're in the northern hemisphere, the days would be longer in the southern hemisphere. So that effect produces major variations in the output of a solar array. So to highlight this for you, that array that I showed you earlier produces about twice as much power on twice as much energy on a summer day due to the longer day and the more direct sunlight than it does on a winter day. So you get about half the power production on a winter day, half the energy production on a winter day that you get on a summer day. So what's happening with the sun? Well, I just a little bit of fun for you there. Inside the sun, hydrogen is turning into helium. So hydrogen nuclei are combining to form helium. This heats the sun's surface temperature to about 5,500 degrees Celsius. And that results in rapidly accelerating atoms on the surface, or even nuclei on the surface, and those radiate energy away from the sun. So that's what we're capturing. We're capturing solar energy, as we're capturing that byproduct of the nuclear fission that's happening in the sun. The orbit of the Earth causes the seasons. The spin of the Earth causes the day and nighttime. And then there's also some atmospheric effects as the sun comes through the atmosphere, where we get some reflection off the surface of the atmosphere, and then there's filtering and, of course, weather caused by the Earth's atmosphere. Let's talk just a second about that. So how much energy is really coming from the sun? A lot, right? There's the majority of the energy on Earth's surface is coming from the sun, about 1,400 watts per square meter, right? So a square meter of energy, a sidewalk square of surface area, if it could collect all the energy, would be getting about 1,400 watts, but that's at the surface of the atmosphere. You have some reflection off the surface of the atmosphere, and then you have some absorption in the atmosphere. And what ends up landing on the surface of the Earth when you're at a typical latitude in the United States is about 1,000 watts per meter square. It's about 1,000 watts per meter square are striking the surface of the Northern Hemisphere at a latitude of about 45. One more thing I'm going to point out, again, I don't want to get way into the details of solar, but if you look and if you had the sun coming straight overhead, there are different types of atomic mass spectrum, or sorry, atmospheric mass spectrum coming from the sun. AM0 is what you would get in the International Space Station. That means you're going through air mass 0. You've gone through 0 atmospheres. You get that on above Earth's atmosphere. AM 1.0 would be if the sunlight comes directly from the sun, goes straight through 1 atmosphere worth of thickness, and then hits your surface of the Earth after going through 1 atmosphere. You might notice that the sunlight color is different in the early mornings and the evenings, right? And so the amount of filtering and the way that the sunlight is filtered depends on how much air it goes through. So typical panel solar production is based on an air mass 1.5 spectrum. So when the sunlight comes through a distance of atmosphere that is approximately 1.5 atmospheres thick, you would get the typical spectrum that is used to produce the power ratings on the back of a solar panel. And I've got one more line in there showing you that in the early morning and the evening, the sunlight comes in at an extreme angle and you get a lot of filtering. And that filtering from the atmosphere, the absorption of different colors, especially the blues and greens, is what results in the sun's color looking at reddish orange in the evening and the early morning. So if you're wondering why that happens, it has to do with the amount of atmosphere that sunlight is going through. So there, you've learned something interesting. Daniel, go ahead.
Before, we just had someone clarifying. So nuclear fission is the splitting of atoms. Nuclear fusion.
Did I say fission?
I believe they caught you.
They did catch me, and it even typed here. Yes, so nuclear fusion, sorry, is the joining of the hydrogen nuclei that occurs in the sun to produce helium. Sorry about that, and thank you for catching it. Great. Okay, so I wanted to point out for you on the back of a solar panel. So this is a typical module. This is a sun harness label on a solar panel that I just grabbed offline. I wanted to point out for you that the standard test conditions are about 1,000 watts per meter squared with an AM 1.5. That means air mass 1.5, so it goes through 1.5 atmospheres. And the reason that's become the standard is that about the amount of atmosphere that sunlight goes through when it hits the northern hemisphere, and the testing was being done in the northern hemisphere. Another thing to point out is that The standard test condition is also being done when the panel is being held at a 25 degrees Celsius temperature. So I said earlier that panels almost always produce less energy than their rating. Well, typically panels are heating up to temperatures closer to 50 degrees Celsius when they're operating, and there's a loss of energy there. There's another thing I'd like to point out here, and that's what is shown on the right side of the screen. This is an IV curve. It's the current on the vertical axis and a voltage on the horizontal axis. So if you are drawing power out of a solar panel by drawing current and having a voltage across the panel, right, you're getting power. If you short it out so that there's essentially no load, right, you'll get the maximum amount of current, and that's what's known as the short circuit current of the panel. So that's what would happen if you took your ammeter, clamped it on your panel, and then just shorted the two wires of the panel together. You should get a current that's typically the short circuit current as long as you have a full sun intensity and you're at that 25 degrees Celsius. You should be able to get somewhere pretty close to that 9.6 amps. The current that is produced by a solar panel depends heavily on the amount of sun that the panel is capturing, right? So this depends on the irradiance, the angle of the panel, but essentially just how much sun the panel is capturing determines how much current the panel will generate. The voltage of the panel, you will be maximum when you're drawing the least amount of current. The more current you draw, the more the voltage comes down. So if I don't draw any current, you'll have an open circuit condition. So the leads on the panel are not connected to each other. That's the open circuit voltage. This depends on temperature. So typically at cold temperatures, your panel is going to have the highest voltage. So if you're installing a system, like for instance, I'm installing a system right now. I have 128 cell panels, so high voltage panels. They're at an 83 volt open circuit, right? So I'm interested in knowing how many panels I can put up in each string. And I'm going to be using a Briggs & Stratton inverter, which has a 600 volt open circuit limit, right? I need to pay attention to how that voltage of my panel is going to vary at cold temperatures. So at extremely cold temperatures, the VOC of the panel, it starts at 83 at 25 degrees Celsius. But if I get a day of 0 degrees Celsius where I'm at, right, that would be extremely cold in California, 32 Fahrenheit. But my VOC would be higher. It might go up to about 85 volts. And you can calculate that. There's on the spec sheet of a panel, they should give you the variation in voltage per degree Celsius. And what you notice this blue curve is showing you is power is the current times the voltage across the panel, right? So the current through the panel times the voltage across it is the power you're getting out of the panel. As I increase my voltage and my current, right, I'm going to get the maximum power point. So if I follow the curve of my panel and start putting more resistance on the panel, more load on the panel, I'll get less current. Eventually the current starts to drop down, but eventually I'll get to a maximum where current and voltage is maximum. That's known as the maximum power point. And the equipment is supposed to track that. Power production from solar panels depends on the effective surface area, right? So if I have a panel that's not directly pointed at the sun, the area of the panel, right? Let's suppose I had a 1 square meter area panel. On the surface of the earth, 1 square meter would be approximately 1,000 watts striking that panel. But if that panel is oriented away from a perpendicular direction towards the sun, you have less effective area. In fact, the area varies as the cosine of the angle between the sun rays and the orientation of the panel. So that's another reason why, right, you would want to track the sunlight. You would want to have your panels perpendicular. However, we're really not doing this anymore. Panels are cheaper, right, now than they used to be. And tracking equipment is expensive. And then another downside to this is the tracking equipment means that you have to have more room for your array, right? Because you have to have more room for your array because the panels have to move. And if you get them too close to each other, they're going to be shading each other. And so tracking is not very often done. In fact, I'd be curious if any of you are installing tracking systems. The exception to this is people are still doing kind of pole mount tracking systems, but not on a roof setting. So I'm curious if the installers out there that are on this call are still installing tracking-based systems.
Yeah, Nathan, that's a good point on tracking. You know, it's just more things to break. And one of the pole mounting systems that I've always was kind of amazed by was, I think ZoneWorks had made one where they have tanks of refrigerant on either side of the array that would boil off and move to one side or the other, thus making it track. So if anybody's done one of these systems, please put it in the comments. We'd love to hear about it.
That's cool. That's cool. There's another way you can do this too. It's a very similar design with wax. So there's a wax-based pistons that are actuated on temperature, and so they're oriented such that the cylinders are either in the sun or not in the sun, depending on the time of day. And the wax-actuated cylinders can do something similar. But again, tracking is fairly uncommon now. I didn't want to spend a bunch of time talking about it. Just, you know, it has been a major topic in the past. What I'm showing you here is kind of a combination of weather, atmospheric conditions, filtering, and this is the solar irradiance data from the National Renewable Energy Lab. And what you can see is this gives you the number of full sun hours. This is direct normal irradiation, and it's the amount of solar that's received by a unit of surface area that would always maintain a perpendicular orientation to the sun's rays. So if you had a 100-watt panel and you were tracking the sun as it moved across the sky, and you always kept the surface area of that panel normal to the sunlight that's coming in, that 100-watt panel, if you're at a location where you would have 5.5 kilowatt hours per square meter per day, that 100-watt panel would get about 5.5 times 100 watts of energy, right? So this is telling you, what you can see is a lot of people in the north think, well, you know, I'm way different from California. I'm in the north. I'm not going to get that much energy. For instance, my mom lives up here in northern Pennsylvania. My sister lives in Buffalo. But there's not as much variation as you think, right? As you might think. In the north, you're still getting a similar amount of solar irradiation, typically maybe 4.5 instead of 5.5. So you lose maybe 20% compared to the best locations in the US. It does depend on weather, and this map helps to understand that.
And Nathan, before we go off that map,
yes, go
just
ahead.
so I understand, when I kind of come from the off-grid world, and I have a similar map, but my map shows the solar irradiance for the worst month of the year, which helps
yes.
me design a solar system that helps somebody get through the winter. Are we looking at a map that's averaged for the year here?
Thank you, Daniel. Great point. Yes. So what you're looking at here is an average throughout the whole year, right? So on a summer day where your days are much longer, right? You could have a 14-hour day instead of, you know, in the wintertime, you might end up, you know, with a 10-hour day. So you've got longer days in the summer. And so this is a 12-month average. And Daniel's exactly right. If you're in the off-grid world and you want to make sure you have enough power, you have to make sure you have enough power in the winter. That, or you have a generator, right? And you can angle your panels more, you know, farther, steeper towards the south to capture a little more energy in the winter and help deal with that extra energy production you're getting in the summer, you know, so that you can try to balance the winter to the summer a little bit more.
Couple of comments. Somebody, Drew had mentioned All Sun of Burlington, Vermont has very cost-effective trackers popular in the Northeast. So cool. Thank you, Drew. Drew also mentions he says direct solar ignores diffuse, which can be 40% of the output. No, it's only 25% difference from best to worst. I'm not sure.
I think, Drew, you'd have to show that to me. So diffuse solar is very low, and typically you're not getting much when you have cloud cover, etc. I doubt it's 40%. And I can tell you just from the testing that I had done when I was in graduate school testing solar panels, typically I would lose something like 85 to 90% when I had diffuse sunlight compared to having a direct line of sight to the solar radiation coming down. But I'm happy to be corrected if you want to share some of that information with us.
He apparently in Vermont, he believes it's closer to 40%.
Okay.
And another one, just to prepare us, somebody's asking about our BESS cabinets, whether they're weather resistant, whether they're waterproof, and they're working in Canada, so they need a solution for extreme weather conditions. I know we got a couple slides on that coming up. I did also want to bring up that on June 8th, we're going to have an entire training called Installing in Harsh Environments, where we dive deeper into that.
Awesome. Thank you, Daniel. Yeah, I will be showing, let me hold off on the BESS question. I'm going to show some of those cabinets here in just a second. I want to show you, this is a typical fixed home array power production curve. And the current array is only 1.5 kilowatts. And what I'm showing in red there is the demand of the house during a day, right? And you can see that the demand hovers a little bit under 1,000 watts. Maybe it averages something like 900 watts, so a little under a kilowatt for 24 hours. So you're looking at maybe 20 to 22 kilowatt hours of total energy usage during the day. The amount of energy you're getting from the solar array is the area under the curve. It's the product of the time, right, times the amount of power that you're producing during that time, right? So the number of kilowatt hours you would get. And so you can see that that original green curve, you're only meeting your load demand for a very short amount of time. And in fact, most of the time, the solar is only producing some of the net needed power for the loads. By increasing the size of this array to a 3 kilowatt hour system, we're getting more effective surface area, or more effective area under the curve and closer to matching the full demand of the house. I would argue to go even bigger than that. And the reason I would argue that is putting a 5 kilowatt array or a 6 kilowatt array on the roof is you're getting more watts for the dollar, because a lot of it is just the fact that, you know, the cost of getting somebody up on the roof and producing that energy. The other reason I would argue to go larger is once people start getting solar energy at low cost, they start adding more electrical appliances and getting rid of other gas powered appliances, etc. I want to talk briefly about how to conceptualize solar energy and power generation from solar to homeowners, right? And one of the things that I'm going to use here is a water analogy. So what's shown on the left side of the screen is actually an install that I did with students from California Polytechnic State University in Ghana. And you'll see on the left side, there's a community center there where we have 435 watt panels, and then there's a water tower. What the solar panels on this water tower are doing, there's a little under 1,400 watts, I guess, on the top of that tower, is they're sending power down to a pump controller, and that pump is pumping water up into that water tank that's on the top of that tower. And then there's a filtration system, and then that water is delivered below as filtered water for the village. So I want you to think of energy production, and the analogy here is that energy is water. Right, so water is the number of liters, energy is the number of liters of water that you have. The power produced by the panel is how quickly you're delivering that energy. And so the solar panels can be thought of in a way like water pumps, right? They're only actually giving energy when the water is actually flowing. So if you're not using the energy that a solar panel is capable of producing, you're not actually producing any energy from that panel. Power is there, but if you're not opening a tap to deliver that energy somewhere, you're not using it. And then the solar panels as water pumps, the water tank as a battery, right? So it's a pretty good analogy. You could take it even farther, right? You could say that the pipes are like wires, loads are like water taps draining the energy from the system. You could even say voltage is like the pressure in the lines, all right? So, question for you. There's a solar array on this roof, right? If all the loads are shut off, how much power is the array producing? You've got a 4 kilowatt array shown on the roof. If there are no loads and we're not feeding back to grid, right, no energy is being produced. So those panels are sitting in the sun, but if they're not powering a load or sending energy back to the grid, you're not getting your money out of your solar array, right? So what do you want to do? You want to be able to, if you don't have loads on in the house, you want to be able to store that energy in the form of a battery, or you want to be able to get some money from the power company by sending it back to the grid and letting somebody else use that energy. As Daniel talked about in the very beginning of this talk, solar feedback credits are greatly reduced now in California. And then of course, they don't even exist in many other places. So you need an energy storage system, you need a battery system. And the inverter is really the central part to that. We'll typically break up systems so that we don't have to have a huge inverter and a huge battery bank. We'll do a backed up loads. So you want to keep that refrigerator on, the lights on, your internet connection there, maybe the television, but maybe some other things like maybe you have a furnace where you have a blower. Maybe you don't need that backed up. Maybe you don't need some of the other things backed up, like an electric dryer in your house. And so we'll put those on loads that are kind of optional. So critical loads, what I'm showing here is typically just a simple single line diagram of how a Briggs & Stratton inverter or another hybrid inverter could be wired. A hybrid inverter typically has the charge controllers built into it, has the ability to connect with the grid, and has the ability to charge batteries. And so typically we'll bring energy from the main panel into that inverter, and then we'll allow that inverter to back up critical loads. It's important to identify, especially for your customer, what loads are core, which ones are important. And we go through with your customer and say, okay, what things do you want? You know, lights don't take much power at all. We typically would put all the light circuits on backed up loads. Definitely want your internet connection to be on there. Many homeowners will want the TV, definitely have that refrigerator on there. But some of the other things, as I said, some of these appliances that you're not using as often, maybe you're not going to have that electric range available. You just have the microwave on the backed up loads, depending on how big your system is. Similarly, if you have an electric water heater, maybe that's not as crucial that you have that electric water heater on there. The hot water, if you use it sparingly, will typically last a while. And so identify with your customer which loads they want. So what I'm showing you here is the energy that is used in my house on a typical weekday. And one of the things you'll notice is I average a very small amount of energy. I'm typically using only 400 watts, less than that on some hours during the day. And so I'm averaging something like 450 watts over a 24-hour period. So during a typical day, I'll only use about 10 kilowatt hours of electricity, right? And there's some variations. Some days, like today, I'm a wimp. I have an electric heater at my feet keeping me warm. But I'm not using a whole lot of energy, so why am I bothering to put a solar system up on my roof, right? Well, there's also some variation throughout the year, right? I use more energy in the winter months. Why do I use more energy in the winter months? Well, typically the heater's on in the winter months. I don't have electric heat, I have gas heat, but I have a blower motor, and that blower motor consumes a decent amount of electricity. Also spending more time indoors. In the winter, using more appliances in the winter. And so there's some seasonal variations. But once again, like why would I want to have solar? Well, I'm thinking ahead, right? I'm only using 300 kilowatt hours per month. Average that at about 25 cents per kilowatt hour. It's a high electricity bill if I actually pay $75 a month. But I currently have a gas bill, right? I have a gas water heater. I have a gas range and oven in my house. I don't have a cooling system in my house. So if I had access to cheaper electricity, I would probably switch my water heater to a heat pump water heater. And actually there are tax credits that you can get for installing energy efficient things like a heat pump water heater. I will probably install electric heating through a heat pump. And that's these mini split units could allow me to cool and heat my garage, right? They're reversible. So you can either use them as a heating unit or use them as a cooling unit. And many of these systems are very low power draw and can move significant amounts of heat. So for instance, the little electric heater that I've got going right now is 100% efficient, right? It converts, it uses 1,000 watts and it produces 1,000 watts of heat. But a heat pump can actually operate on a high coefficient of performance. And so you could use 1,000 watts of power, right, for an hour, so 1 kilowatt hour, but you could actually move a lot more heat than that. You might be able to move 5 kilowatt hours worth of heat. So heat pumps are much more efficient, especially depending upon the conditions. I also might switch to an electric range, and then thinking ahead, I would probably like my next vehicle to be an electric vehicle. I've got a diesel truck right now that I use for a work truck, and then a gasoline powered car. And I'm sick of working on gasoline powered cars when things go
Nathan,
wrong.
yeah, no, Nathan, I always get the pushback from homeowners when I say, you know, let's make you go electric. And people say, well, I love to cook with gas. And I hear that a lot. And I love to cook with gas. And I say a lot of times, well, keep the gas range in a lot of cases, because really, if you think about the amount of gas consumption compared to some of these other systems, so which ones would we want to tackle first here?
I'd have to be honest, I love cooking with gas. And I you know, we switched from an electric range to a gas powered range recently when we moved, and I prefer gas. But like you said, you're not using it that often. So probably the first thing for me would be to switch my water heater, because I enjoy warm baths and my daughter enjoys warm baths, and we actually use a decent amount of energy powering that water heater. It's burning a lot. I also, my wife is from West Africa, and I am a wimp about the cold. I keep my house about 75 degrees. I would probably want to put in one of those mini splits, because my gas bill in the wintertime tops $300 per month, and that's a significant cost. So those would probably be the first ones I would do. I don't have an electric car yet, so electric charging system for the car and the range would probably be last. It's a great question. Yeah, thank you. A couple things. Somebody mentioned, you know, induction can people that aren't necessarily used to electric, they could try that out, and it works very similar. Somebody also mentioned that your average of 400 watts is pretty low, and maybe a closer average is 1 kilowatt. Going back a little bit, somebody had mentioned solar modules. Are there certain solar modules that are better able to capture diffuse rather than direct sun? There are bifacial modules that can capture diffuse energy from below as well as above. And I have to be honest, Daniel, I'm not an expert at that. You know, I would imagine that the answer is yes, but I'm not sure. Do you have any more information on that? No, we'll have to look into that and get back to you. Another comment, going back a little bit, that, you know, somebody was talking about out in Iowa, they have these utility-owned solar farms, and a lot of these solar farms do have tracking, but they have what's called single axis trackers. And can you maybe talk to a little bit about what's the difference between single and dual? Right, the sun moves the most from throughout the course of the day, right? And so you really only need to have something that's able to point to the east in the morning and the west in the evening. And so for a large scale array where you can move just a single, you know, a single axis, so you're just kind of pointing to the east in the morning and the west in the afternoon, you orient your array so that it's along a long axis north-south, and then you just tilt that array. And I have that in the solar farms outside of my town here in San Luis Obispo. And yes, that does make sense, and it's a fairly low cost way of tracking. And it's typically done on larger systems. And I would say if you have a big enough area to do that, that might be a cost-effective way of adding backing. So I want to say something about the tax credits, right? Because there are the IRA and the ITC has increased the taxes incentives, and there are special tax deductions for adding things like batteries. You don't even need to add solar to get tax incentives on a battery-based system now. Another thing to point out is the heat pump water heaters, right? Energy efficient heat pumps can also get, I think it's up to $2,500 for that install. So you can get savings right now from taxes. It also gives you energy independence, right? So I had a power outage. I've had a couple recently, but one recently that took down my internet. It was late at night, so it didn't matter much. The fridge went off, but it came back on after a few hours. And Daniel, one more comment. I don't have the slide on here, but the person that says, yeah, my number of 400 watts on average is low. It is. Typical average across the entire US, I think, is 916 or something. It varies a bit from state to state. Obviously, it depends on where you are and what other types of energy are available. So this is what I'm going to use for the system I'm putting on my house. These are amplified batteries, which are communicating batteries, which can communicate to the inverter. I'll come back to that question that we had about temperature. I need to be a bit mindful of time here, so I'm going to go a bit quickly. I'm going to be using our Briggs & Stratton 6 kilowatt inverter. This allows me to add a generator in and have control over that generator through the inverter. It also has Energy Track app and allows me to monitor my system remotely through an app, as well as make system level configuration changes. I'm not currently installing a generator, but there's the potential to do so in the future. So this is a DC coupled system. What you can see there are rapid shutdown modules that I'll be putting on my SunPower solar panels. There's a rapid shutdown button at the inverter. Amplified battery bank, just 3 batteries is enough to give me about 12 kilowatt hours of storage. And since I'm only using about 10 kilowatt hours of battery energy over the course of a full day, it should be enough for me. I'm going to use a critical loads panel, back things up in my house that I want to stay on. And maybe in the future, I'll add a generator if it proves necessary.
Nathan, I did want to point out, go back one slide, please, is that generator has a 2-wire start capability. So our inverter can actually automatically start and stop that generator based on the battery state of charge. Additionally, yes, what we're looking at there is a generator that would be connected to either propane or natural gas line.
Yeah, and then the other nice thing about having that generator there is generators are typically operating at their highest efficiency when they're mostly loaded. So when you're around 90% load, the generator is producing energy the most efficiently from the fuel that it's using. So if you load that generator and you're able to supply all the loads to your house, you're also charging the battery, you're able to shut that generator off more quickly. So if you do need a generator, even in an off-grid setting, right, having batteries there allows you to get more energy out of the same amount of fuel from your generator. So good point, Daniel. So when we're talking to the home energy about energy versus power, right, kind of pointing out to them that you can think of the batteries as the fuel tank of the system, and you can think of the inverter like the engine of the system, right? The inverter is taking the energy from the batteries and converting that into usable power. This particular generator is able, or this particular inverter is capable of surging up to 12 kilowatts for a brief period of time, 9 kilowatts for up to 10 seconds. And it also acts like a unlimited power supply in that you have a very short transfer time. So what are the primary drivers for the market? More and more people are switching things over to electric. Obviously, the big one is cars, but there are other things like heat pumps, mini splits, heat pump water heaters, electric ranges. Induction cookers are great that direct heat to the pan, right? So it doesn't take as long to warm up. And so there's been a rapid demand for energy storage, and just last year it grew by 80%. This is probably only going to accelerate, especially in places like California, where the feedback credits are essentially disappearing. You're getting so little for the kilowatt hours you sell to the utility. How do typical homeowners use their energy? I think it's important when we're talking to homeowners that they understand where their energy is going. A lot of homeowners might think, oh, my microwave's a big energy hog, because it uses 1400 watts. Well, if it's only on, 10 minutes during the day, it's not going to use a lot of energy, right? You might get some demand charges if you had a bunch of microwaves running at the same time. But for the most part, right, it's things that are running constantly throughout the day. Your refrigerator, electric water heater, electric dryer, things that are running for longer periods of time. And it often doesn't get thought of, right? But the blower motors on even, your natural gas heating, propane heating, etc. Water heating is a big one. Lighting is getting smaller and smaller as almost everybody is moving to LED energy efficient bulbs. TVs typically don't use much. Typical TV, plasma TVs are a little bit higher power consumption, but consult with your customers, right? Consult with them, figure out where their energy is going and what things it might make sense to change, right? Especially when there's tax incentives to get things like new water heaters in there that can produce, that can heat water a lot more efficiency and use electric when that electric energy on the roof is free. So my monthly energy consumption looks something like this, right? I'm rarely using more than 300 kilowatt hours over the course of a month. I know that, as somebody said, other people use more. There's not much seasonal variation for me. There's a bit of seasonal variation, but because I'm very close to the Pacific Ocean, temperature doesn't really change that much. If you look at the temperature on my screen, it's pretty much averages about 60 year round. This is a home in the north, and you can see a big difference. So I'm showing you right there natural gas energy use at one of my colleagues up at the Briggs and Stratton headquarters. He lives up in Wisconsin, and you can see his natural gas obviously in the colder months goes way up, and then the electricity goes up in the summer because of his air conditioning. So it's important. Most energy providers will give you this data and be able to provide you pretty high resolution data on your energy consumption. There are also different meters that you can put in the house to monitor your system, and some smart devices. Daniel, are you aware of some of the smart devices? I'm blanking on some of the names of things that can figure out your energy usage and identify what's using it.
Yeah, and that kind of brings up another good question. Somebody had mentioned, what are your thoughts about programmable circuit breakers and programmable load panels? And part of those technologies and products not only allow you the ability to drop loads and add loads based on how much energy you have left in your batteries, but also gives you a better visibility of what these loads are actually consuming over time. I'm always thinking of the kilowatt meter. I don't know if anybody remembers that. It's a little household
I've
plug.
got one of those in my garage right now, Daniel.
So,
yes, the kilowatt meters, new panels like the span panels and lumen panels are going to play a big role, I think, in home energy monitoring, home energy use and control, right? It gives you that, again, it's giving you that flexibility to decide where you're spending your money on your energy. Our transfer switches, the Symphony 2 allows you to have load control, right? When you're running off your generator, you have the ability to drop different loads like air conditioners, etc. So yeah, I think those kind of panels are going to be, having smart panels makes a lot of sense. And in fact, we're communicating with Lumen about getting integration with our inverter, which you see here. So we've got a lot of different energy solutions. Some of them we've had around for a while, some are newer. What you're seeing here is our newer ESS, which is our inverter paired with some of our batteries. You see a battery cabinet there on the left. our energy app, energy track app there in the top left. And then these are indoor or outdoor rated. The larger wall mount batteries are outdoor rated batteries, so this inverter can be installed outdoors. We'll talk a little bit about cold weather, but as Daniel said, we have a whole training coming up on that. So these are the charging characteristics of the batteries. It's important to note that our batteries are rated at C/2. And if you're doing a charge from 0% up to 100%, what that means is the fastest you could charge these batteries safely would be 2 hours. The batteries are also have a certain amount of output capacity, and they're also, for a continuous output, discharge at a C/2 continuous rate, which allows you to get about half the energy stored in the battery out in a given hour. They, however, can surge. So a 3.8 kilowatt hour battery, the Amplify battery, can actually produce 4 kilowatts for up to 10 minutes. And when paired with a communicating inverter, you have this full ability to surge. We have these outdoor rated NEMA 3R enclosures. These are watertight installations. So these can be installed outdoors. Again, you have to pay attention to temperature. These units can come pre-programmed with Solarc or a Schneider inverter, as is pictured in the right. We call that our access cabinet. And this is a pretty easy plug and play installation. I need to wrap up. We're just out of time. If you do have questions about temperature, our communicating batteries can actually charge down to -20 Celsius at a slow rate. As they charge slowly, it starts to heat that battery up, and the charging can occur faster. So we actually have a solution as long as you're using one of our communicating batteries for low temperatures. We have another solution, which is an integrated heating pad, which can heat the batteries based on internal temperature, but that does use some electricity to do that. Finally, as I'm closing off here, I want to highlight, we have a Simplify Elite Installer program. And so if you're not part of our Elite Installer network, we encourage you to do so. I'm showing you Elite installers here from around the country as well as the world. If you sign up for this program, you'll receive a free welcome package with swag. You'll earn $25 cash back on batteries, and you're also eligible for special Elite Installer only promotions. We currently have a beta testing program that some Elite installers are participating in. And you get recommended to customers by our sales team. So if you're one of our Elite installers, the first thing we do is we try to find an Elite installer in the customer's area to recommend to them when they call in asking for help. You'll also have access to co-branded marketing material, and you may be featured in our social media posts or our monthly newsletter, our Intelligencer, and these go out to many thousands of people. So consider signing up for that. I also want to highlight a lot of the information that's available on our website. We have installation manuals here, but we also have integration guides. So suppose you're installing our batteries with maybe a Sunny Island inverter or a Solarc or a Magna. So you can look up the integration guides, and oftentimes we'll show you step by step in the way that it actually appears in their menus, how to program their equipment to work with our batteries. So I'm a little over time. I think it's a couple minutes after the hour. I really want to thank you for your attention. If you have questions, please email us, training@simplifypower.com. And if you have questions about an install or a project you're working on, you can either email Daniel or I at training@simplifypower.com, or you can reach out to our application engineers. We have sales application engineers, 805-640-6700. Hit extension 2 there to get the sales engineers, and they can help you with planning a system. So this training is not yet NABCEP certified training. So I won't be able to issue NABCEP credits today, but it should be NABCEP approved in the near future, and keep an eye out for other trainings. So Daniel, are there any questions we should answer here at the end?
Yeah, we have a couple ones. We're going a little bit back to the energy monitor. Somebody had mentioned the Empora View energy monitor, and I always like sometimes the idea of putting an energy monitor on somebody's house before they go solar. Ideally, you'd have to do that for an entire year, but it gives you an idea of what they're consuming. Not everybody can do that. Some of these energy monitors are capable of only capturing the entire home's loads and not give you that more granular granular detail that you might see with some of those smart panels. Somebody also made an observation that anytime something gets more complicated, like a smart load panel, there's more things to break.
Yes.
And
Sure.
we see that with trackers as well. Somebody had also kind of made the observation about the deferred cost of paying for gasoline for an EV car, and considering somebody's paying $4 or $5 a gallon, definitely you can see some cost savings there. Another one, I don't know if these are really questions, but maybe this is a good one for you to.
Comments too are great.
Comments, yeah, too are great. So we had talked a little bit more about how diffuse solar panels work, and somebody had commented about some of these modules can handle more of the light spectrum wavelengths, and kind of going into the not visible light spectrums as well.
Yeah, that's actually something that I worked on during my dissertation. We worked on, we were using polymers to create solar cells, and something that I didn't get into is longer wavelengths. So when of that 1,000 watts that strikes per square meter, we're typically only getting about 20% of that energy. There are a couple of things that play into that. One is the voltage of the solar panel is based on the band gap of silicon right now, which is about 0.6 volts per cell. And if you capture more light, you have to have a lower, you end up with a lower voltage. But you can have multi-layer solar panels, and typically in organic solar panels, you have stacked absorber sections where you're looking at one is absorbing longer wavelength and another one is absorbing shorter wavelength. And that's an important point that is often glassed over. Silicon-based panels have there are certain characteristics, but you can do better by looking at different absorption spectra using something other than silicon.
Yeah, great answer. Thank you, Nathan. What's the difference between Phi and Amplify batteries?
So the Amplify battery, that's a great question. The Amplify battery is more expensive, but you get more from it. So the Amplify battery also has a more sophisticated BMS, right? We've got the same premium battery cells in there, but it's got a more sophisticated BMS that allows you to do temperature monitoring, and it allows it to communicate with inverters and other charging equipment to get you to be able to have more versatility, right? So the Amplify battery can communicate with other batteries. It can give you battery level information with our Energy Track app. So you get a lot more out of an Amplify battery. It's also a better battery for cold weather solutions because, as I said, it actually allows you to charge slowly at temperatures below freezing.
And we're going to have on June 22nd an upcoming training completely on battery management systems, where we're going to dive a lot deeper into that conversation. Nathan, is a recording of this webinar going to be sent out?
Yeah, so everybody will get a copy of these slides in this webinar. I will be fixing the fission to fusion mistake there on the screen. So thank you for pointing that out. And actually, you'll get a copy of the recording probably tomorrow. It'll come out to everybody who registered for it. So yes.
Great. We're getting a lot of thank yous. I think we're going to end with one last question, and this is a good one. Are lead options being left in the dust? They have such a great history of low cost and reliability. So what would be an example of where we might use a lead acid? I'm thinking of it just something sitting there waiting for an outage. But if we're in a high cycle environment where we're cycling the batteries, can you speak a little bit to why maybe people, why low cost isn't really a factor when we're cycling batteries?
Well, I will say this, that if you look at the levelized cost of energy, that's the amount of cycles and amount of energy that you store and use over the lifetime of a lithium battery, right? So you get 100% depth of discharge out of a lithium battery. A lead acid battery, you're typically limited to about 50% depth of discharge. And that declines quickly with time. So you're only really getting about 30% of the energy out of a lead acid. If you look at the cost of changing that battery after 5 to 10 years, it starts to make more sense, to the point where if you look at the levelized cost, including installation, all these other factors over the lifetime of the battery, that a lithium battery is about half the cost. There are some applications where lead maybe still makes sense, right? But most companies and most homeowners are realizing that you get more for bang for your buck with lithium. One thing that lead is a little bit better at, right, especially AGM batteries, is low temperature environments. So if you have a place where you're absolutely going to stay cold, right, and you don't have the ability to keep those batteries cycling and heated, or you don't have the ability to shut them off remotely to protect them, maybe AGM batteries still make sense there. But for most applications, I would say that lithium iron phosphate is what you want for home battery storage. Great.
Thank you so much, Nathan. That's all the questions that we had.
Thanks, everybody. I hope you had some fun and that maybe you learned something from this. Enjoy the rest of your afternoon, and we'll see you next time. Bye.